sandwiches as you expect to be able to make. And the same thing happens with chemical reactions. Sometimes things don't work out exactly perfectly. So even though we figure we can make 9 sandwiches with this amount of lettuce, what if 3 of the pieces of lettuce are like wilted? That limits the amount of product we get even further. Or maybe like, I don't know, maybe your cheese, the end slices are a little bit moldy or something. You're like, well, we're not going to use those, but the rest are kind of okay. We'll get by. Maybe we can only make 8 sandwiches. So sometimes it doesn't work out to be exactly right. I'll give you another like example. I don't know. A couple of years ago, there's a person who works here who was like, "All right, I got this shed, and the shed has like a roof, and they wanted to put new roofing material on top. And this it's kind of a simple problem in geometry, and I don't even know why they had to ask me. But um, let's say the dimension of the roof is this is 6 foot, and this is 13 foot, so it's 6 feet and then 13 feet. But the pieces of roofing come in sheets that are 4 feet by 8 feet. Now, you might first say, well, let's just figure out the area of the roof and figure out the area of the panels, and then just divide the area of the roof by the area of the panels. That'll tell you how many panels you need. Except you might see here that because there's this 6 foot length of the roof, when these roofing panels, when you purchase them, you're actually going to cut off that 2 feet and kind of get rid of it. And similarly, because they're 4 feet long, you could line up 3 of them, but that only gets you 12 feet. You got this one other little foot out here you got to deal with. So it turns out you need 4 panels of roofing to get across this area, even though you're going to throw out the top 2 feet of every panel, and the last panel, you're actually going to throw out 3 of the 4 feet of the side of it, which is kind of a lot of waste of material. In other words, you could cover the roof with 3 panels if you do it just by area, except the problem is you end up cutting off pieces and kind of wasting them. In some ways, in chemical equations, chemical reactions, you get other products that you're not looking for, or you have amounts of waste. You get what are called side products. And sometimes not all the reactant reacts. In the case of these roofing panels, you end up throwing some away. So that's kind of like an example of, also like, oh, for a loaf of bread, if you're making sandwiches, there's a heel on both ends. You're not going to like, you're working at a deli. You're not going to be like, oh yeah, this sandwich got a heel on the end. Some people like the heel, but if I'm going to get a club sandwich, I don't expect there to be a heel. I expect the restaurant to like throw that away or make some stuffing out of it, or I don't know, do something else, not serve me a heel. Okay, so this reaction, copper and sulfur makes copper sulfide, copper 1 sulfide. It is critical that the equation is balanced. So if you balance the equation, you got to put a 2 in front of the copper. That's all you got to do. So 2 in front of the copper. So 2 coppers and 1 sulfur get you a copper 2 sulfide. You've got equal quantities, 8 moles of copper and 8 moles of sulfur. How much copper sulfide do you end up with? So the quantity of copper you start with, 8 moles of copper. Let's see, 8 mole of Cu. In the chemical equation, it looks like for every 2 mole of copper, we make 1 mole of copper 2 sulfide, or copper 1 sulfide. And that comes out to be 4 moles of copper sulfide. You also have the 8 moles of sulfur. So with 8 moles of sulfur in the equation, for every 1 mole of sulfur, you get 1 mole of Cu2S. These numbers in the mole ratio are just whatever the coefficients are in the balanced equation. It might seem obvious to you that because you need twice as many coppers for every sulfur, and that you have the same amount of copper as sulfur, you're going to run out of copper first. This is the lower quantity of product that's made, so that means that the copper must be the limiting reactant. So not only is the copper limiting, so the copper is the limiting reactant, I also want to know how much of the sulfur is the excess reactant, how much of the sulfur is left over? In other words, how much sulfur does not get used? And the way to solve that problem is because we know that you can make 4 moles of copper sulfide with the amount of copper that's present. To figure out how much sulfur is necessary, you could take the amount of actual product that's formed, 4 moles of copper sulfide, and convert that back into amount of sulfur. For every 1 mole of copper sulfide that's formed, we need 1 mole of sulfur. So 4 moles of sulfur ends up getting used. This example, it's 4 and 4, so it's not the best example. But this is the amount of, so you need 4 mole of sulfur to make the reaction happen. And that means there must be 4 moles of copper sulfide, or 4 moles of sulfur remaining. 4 mole of sulfur remains, like unreacted. It's better if the example is not like with 4 and 4 or whatever, but with a different, different quantity. So in other words, like if we needed 3 moles, there would be 5 moles left over. Just the same as when you're making the sandwiches and you use up some ingredient, you got some ingredient left over. In the example there, we got the 19 slices of lettuce, which is the limiting reactant. We can make 9 sandwiches. Once the 9 sandwiches are made, there's still a piece of lettuce left over. You can, like, I don't know, have it for a snack, save it for later, give somebody a bonus. Maybe you got a sandwich that's got a couple little pieces of lettuce, throw a third one on there, like bonus lettuce. So this one, not really a limiting reactant problem, but just another example of what's critical to always do. Always, always, always be sure that the equation is balanced to start out. So aluminum and oxygen form aluminum oxide. Aluminum metal in the presence of oxygen in the air corrodes a little bit and forms aluminum oxide, which is kind of like a whitish kind of coating. It's kind of like aluminum rust. This reaction has to have a 2 in front of the aluminum oxide, then a 4 in front of aluminum, and a 3 in front of the oxygen. So that's the correct balanced equation. If it's not balanced correctly, you cannot get a correct answer for anything, because every single stoichiometry conversion involves a mole ratio. That mole ratio depends upon the coefficients in the reaction. So how much aluminum oxide should form if 23.5 grams of aluminum reacts with oxygen? And here you assume the oxygen is in excess. The oxygen is probably coming from the atmosphere. You got plenty of oxygen. So all the time you start out with whatever quantity you know, 23.5 grams. And if you don't start with moles, the first thing you do is convert to moles all the time. So to convert from grams of aluminum to moles of aluminum, you just use the formula mass on the periodic table. I don't know what that is. 26.98. And we're trying to figure out grams of aluminum oxide. So the next step is to convert from moles of aluminum into moles of aluminum oxide. And in the equation, for every 4 aluminums, you get 2 aluminum oxide. So for every 4 moles of aluminum, you get 2 moles of aluminum oxide, Al2O3. But we want to know the mass in grams of aluminum oxide. So finally, you can convert from moles of aluminum oxide into grams of aluminum oxide. So you got to figure out the mass of aluminum oxide. 2 aluminums and 3 oxygens. $101.96. All right, so then altogether the math is 23.5 divided by 26.98. That'll be pretty close to a mole. Times 2 divided by 4, it's close to half a mole. Times 101.96, it's going to be somewhere around 50 or so. Maybe a little less than 50. 44.4. And to assess how many significant figures you should have, just look at the number of significant figures and the value of the quantity, either the mass or the volume or number of moles. That's the amount you're starting with, 23.5 grams. You should get 44 grams of aluminum. Okay, so here's a big concept about what really actually happens in a lot of chemical equations. Let's say that that chunk of aluminum is like a solid chunk that's real like large in surface area. And it turns out that bare aluminum in the atmosphere reacts with oxygen, and you get the coating of aluminum on the outside, aluminum oxide on the outside. So what happens is when this big chunk of aluminum is allowed to be in the presence of oxygen, the outside reacts. And the outside of the metal ends up to be, corroded, and you get aluminum oxide on the outside. But the aluminum in the middle never has the opportunity to react with the oxygen. So if it's a big solid chunk, and even if you wait like forever, you're never going to get all of the aluminum to react with the oxygen. So a good example of that in real life is like a penny has a copper coating, but that copper corrodes. It gets like a darker color, maybe turns like green. But underneath that coating, there's still pure copper. If you take a hacksaw and cut that penny in half and look in endwise, it's still nice and bright inside there. So it isn't like the entire penny has reacted with oxygen to make copper oxide. That's not true. And in fact, for aluminum, aluminum is commonly used to make like the structure of aircraft. That frame of the aircraft is intentionally allowed to just get that little bit of corrosion. And that aluminum oxide coating is actually protective for the aluminum that's underneath because it acts as a barrier to prevent oxygen from getting in. So what should you do to that chunk of copper if you want, or that chunk of aluminum if you want more of it to react? Yeah, smaller particles, like cut it up. If you even cut it in half, now you've got those inside surfaces. But what if you powder it? What if you grind that aluminum down so it's like a powder? Then you get even more product that's formed. Ultimately, you've got to get it down to the level of the individual atom to be able to react with the oxygen that's present in the atmosphere. So making all of the aluminum react is tricky because even if you have a little tiny piece of aluminum, it'll still get that aluminum oxide coating on the outside, and the middle part will be unreacted. So the reality is to make a chemical completely react with another one requires the atoms to come into contact, and for this would be what's called a dry reaction. You don't make this reaction take place in water, so you can't get it down to individual atoms or ions. Making the aluminum completely react is actually like relatively tricky. I'll show you a chemical that I buy. There's one factory that's in Germany that makes hold on, bulk. Let's see, new share, bulk reef. We end up with excess amounts of phosphates in our aquarium system as a result of the food that we feed for the fish. And I buy this product here. It says granular ferric oxide. Well, ferric is like the element iron. Ferric, like the symbol for iron is Fe. And it looks like this. It's like a finely powdered granular product. Iron oxide is rust. I buy bottles of rust and it's fairly expensive. Like this little can, that's the 1 pound size, it's 42 bucks, but it's pure rust. So there's a factory that's in Germany that takes iron and powders it to a very, very, very fine powder and burns it in a high oxygen environment to allow as much of the iron to react as possible. And then that iron oxide, which is a very, very, very fine powder, almost like a mist, is then pressed into these little pellet cakes. And that way, it's as pure rust as possible. So what happens is the iron oxide reacts in a single replacement reaction with phosphate. So iron oxide plus phosphate ions make iron phosphate, which is insoluble, and it puts oxygen into the water. What we can't have happen is for iron, pure iron metal that's unreacted, to be in our saltwater aquariums, because that iron forms iron ions and it will kill the coral. So it turns out we have to have, like usually people don't want rust. You're trying to prevent rust. You're painting surfaces to stop rust from happening. Rust, like rust out your vehicle, and rust ruins metals. So I'm trying to get as much rust as I can with as little iron as possible to take as much phosphate out of the water as you can. The other reason why this product is expensive is the main purpose of it is for, what do they call it? I forget what the name of the process is, but this is used in dialysis. So people who have kidney failure and they're undergoing dialysis, their blood is passed through this product, iron oxide, to take out phosphates and nitrates from your blood and put the pure blood back into your body. And so partly the reason why it's expensive is this is actually medical grade stuff because only one person makes it. And I figure, well, if it's good enough to do dialysis for a human being, keep them alive, it's probably good enough to stick into my fish tank water. So and there's not a big market for it. It's used in dialysis and it's used in like fishy tank stuff. So getting the total amount of product that you want can often be tricky for a bunch of different reasons. The other thing that happens in chemical reactions is you get what are called side products. Not all the time are chemical reactions as neat and orderly as you want them to be. You get products that you don't want. And I gave you a paper. I picked up the paper on the way in, and in the folder, hold on, let me get to the course. Course, Chem 1. Let's see, new share, Safari. Okay, in the folder for this week, at the bottom, here we go, 3.8 to 3.11. At the bottom, it says honors chemistry percent yield outline, and then percent yield worksheet. So the percent yield outline, if you have that, or if you're remote, you can look at it. Describe some important concepts about when chemical reactions happen, what kind of products you end up getting, and let's see. Gotta get to this. Okay, so the concept of percent yield, kind of like, if you get a grade on something, a grade is like what percent right you get out of, the total amount that's available. The same thing happens with a chemical equation, a chemical reaction, and that's that you expect a certain amount of product, but you might get less than that. And as a result of getting less product than you actually want, your percent yield is not 100%. So hold on, let me add a page here. I want to copy this in something else. Today at new share. Okay, so for instance, let's say that, you've got some kind of a paper you're writing or an assignment, and let's say it's like 10 points available, and you were in 8 points. To calculate like what percent you get, you just take the number of points you earn and divide it by the number of points available. 8 divided by 10 is 0.8, and that's an 80%. So if you earn 8 out of 10 points, you get a score of 80%. The same thing happens with a chemical reaction. So let's say in that example that I gave you, we're going to take iron, we're going to react it with oxygen, and we're going to try to make iron oxide, Fe2O3. And so to balance this equation, let's see, a 2 here, a 3 there, and a 4 here. So for every 4 irons and 3 oxygens, we expect to get 2 iron oxides. So let's say that when we make the chemical equation happen, we predict that we will end up with, let's say, 100 or 145.2 grams of the product. This is like a predicted amount. But then the actual amount that we get is like 127.3 grams. We actually get less than we predict. Much like in an assignment, if it's worth 10 points, you don't actually get as many points as you should. This predicted amount of product that you should get, that's called the theoretical yield. The theoretical yield is like the amount that you predict should form as a result of a chemical reaction. So with the quantity of iron we start with and oxygen is in excess, you predict that you get 145.2 grams. The actual yield is the amount, like I guess you could say that you weigh out. So now, why would you not get how much you're supposed to? Well, a bunch of things could happen. Whenever you react an amount of iron with oxygen, it's possible that not all the iron reacts. And some of the reactant is left over as the reaction takes place. So you could have some unreacted reactant. It's also possible here, if you burn iron in the presence of oxygen, you could get other products. You could also, if there's like a smokestack where your exhaust gas is going out, some of the iron could escape through that. It's not always true that you always get exactly what you predict that you should end up with. So the percent yield is just a ratio. The percent yield is the ratio of the actual yield of the theoretical yield. We express it as a percent. In this example, how you would calculate the percent yield is if you take the 127.3 grams and divide it by 145.2 grams, the percent yield will always be less than 100% unless you have a problem with your assumption in the reaction or some other reaction takes place. This comes out to be 0.87672, but you want to express it as a percent with it has 4 significant figures, so like 87.67%. We expect 145.2 grams. That's how much we predict as our theoretical yield. We actually got 127.3 grams. We got 87.67% as much as we wanted to. Percent yields are typically less than 100%. So now, how could you get more than 100%? Well, it's possible that in this chemical reaction, you have other chemicals that are around. So maybe there's a higher mass element besides iron that's present, and oxygen burns with that, and you get products that are commingled, things that are together. It could also be that as a result of your math, you find that you get an actual yield that's bigger than your predicted yield. That can also indicate that you did some math wrong. You predicted the amount of product you should get, incorrectly. So if your percent yield is over 100%, you either did some math wrong somewhere or something else is happening in the chemical equation. The product you end up with, what's critical is that the purity is perfect. The purity needs to be very high, especially for products that are used in pharmaceuticals, in food production. If you end up with a side product that is poisonous in manufacturing the product that somebody's going to ingest or drink or something, you could straight up like, sicken or kill someone. That's not cool. So there's a much higher standard for products that, people are going to actually eat or drink or apply as cosmetics. So that's why we have the USDA for food products, the FDA for both food, well, FDA's, Food and Drug Administration. So they care about both food products and drug products. There's some things that aren't regulated as tightly, like dietary supplements aren't regulated as strictly as drugs. So like, I don't know, products people take for like, athletic supplements, they're not regulated very tightly. A bunch of like vitamins and minerals, like, yeah, just take that, like whatever. Okay, so here's an example. Let me move this up. So here's a reaction, a little different. Iron oxide plus carbon monoxide makes iron and carbon dioxide. So for this reaction, we want to figure out how many grams of iron we should get if 84.8 grams of iron oxide reacts. These are just the formula masses that are provided. So if you take the 84.8 grams of iron oxide, we want to figure out how many grams of iron are produced. The first thing you always do is convert the mass into number of moles, and the formula mass for iron is 55.85 grams. And then the next thing you can do is convert from moles of iron. This is Fe2O3. Oops, hold on. That's not the mass I want. I was thinking about the previous reaction. Iron oxide, sorry about that, 159.7 grams. Iron oxide is 1 mole of iron oxide. The mole ratio, we got to get from iron oxide into iron. And this equation's already balanced. You can double check it. But for every 1 mole of iron oxide, you get 2 moles of iron. The mole ratio from the coefficients in the equation, for 1 iron oxide, you get 2 irons. And then finally, for every 1 mole of iron, the mass is 55.85 grams. So it's 84.8 divided by 159.7 times 2 times 55.85. You always multiply by things in the numerator, divide by things in the denominator. Times 55.85. It's 59.3 grams of iron should be produced. That's what we expect to be produced. In other words, this result of the stoichiometry is always the theoretical yield. But then right underneath it, it says for B, the actual yield was 54.3 grams. We actually got less than we expect, and that's very typical. So this actual yield, 54.3 grams, is less than the theoretical yield. The percent yield is the ratio of the actual to the theoretical. So if you just take the 54.3 grams and divide it by 59.3 grams, 54.3 divided by 59.3, with 3 significant figures, 91.6%. That's a pretty good yield. That's a fairly high rate. It's like with the COVID vaccines, you're like, okay, I want to give this vaccine to a person. We want it to protect everybody. If it's 100% effective, we say the efficacy is 100%. 100% out of everybody is good. And that would be the ultimate prize. But through testing and then now with real world results, even people who get vaccinated um, still contract the disease. But it's a lot closer to 100% than 0%. So it's fairly effective. The reason why it might not be 100% effective is, I mean, you can think of all the little things. What if the quantity of the vaccine administered to the person is not a sufficient quantity for that person's body mass? Because everybody gets the same quantity. It doesn't matter if you're 80 pounds or 600 pounds. It's also injected into a muscle, an intramuscular injection, and your body could defend against that intrusion by forming scar tissue around it, preventing it from getting into your blood. But then people are also very susceptible. So what if you had like open sores and scarring in your lungs and very poor lung capacity, and you got a large viral load from somebody who like literally like coughs into your face who's highly symptomatic? Then you could still like potentially the COVID virus could grow quickly in your respiratory system and overwhelm any kind of immune response you get. So it's not 100% effective, but it's, you know, better than nothing. I would expect probably within a month or so that they'll announce the efficacy and safety for people under 18. And it looks like hopefully by the end of the summer, everybody could get vaccinated. Like everybody, you know, we take off the masks, we're back to normal. We get our shots. Maybe we get some boosters, but we're good to go. So that's the thing about manufacturing, making things. It doesn't matter if it's a chemical equation, it doesn't matter if it's like making stuff. There's always waste, there's always like ineffective things in manufacturing. At the end of manufacturing is always quality control, where you try to like weed out things that aren't exactly perfect, not let them get out to the market. But even still, like you could make 1,000 widgets, they go out to the market and two of them don't work. And people are like, I want to return this, it doesn't work. You bring those back and maybe replace them or whatever. And your yield was pretty close to 100%. It's actually pretty sloppy in chemistry. We don't really get uh, perfect products. In this reaction here, that you get carbon dioxide. If this reaction takes place at a high temperature, you could also like get carbon monoxide plus oxygen. That's possible. And if instead of carbon dioxide, you get carbon monoxide and oxygen, that there's oxygen at high temperature could react with this iron to then form the very iron oxide you start with. So it's possible that this this that happens. It's also possible that the iron and the carbon dioxide could react to form another product. We call those side products. They're products that you can also get as a result of the chemical reaction that are not expected or not perfect. Oftentimes, because when we make chemical reactions happen, we're trying to, make the rate of reaction happen as quick as we can. So you're heating it up, you're stirring it up, and the more energy you add to the reactants, the more and different products you can end up getting, like as a result. Their products have like a shelf life, have a lifespan. It's oftentimes like over-the-counter drugs will have a expiration date, and part of the reason why they have an expiration date is because, well, some of the active ingredients could um, decompose in the decomposition reaction to make the constituent chemicals are made out of. You can also have reactions that take place within the products themselves to make new side products, and you don't get the perfect effectiveness like in the end. I just had like one of those refill bottles for soap to refill like a pump thing, but it was like 3 years old. And when I opened it up, it was like separated into two different columns. And the soap that was at the top was kind of like, it was like a gel. It was kind of gooey and kind of had changed to like a white color. And that's because the top of the bottle is exposed to the oxygen in the air, and the oxygen reacting with the soap caused, the soap to deteriorate. So I got rid of the top part of the soap. The bottom part of the soap bottle was just fine, but the top part was kind of like gross, kind of weird because of the chemical reaction that had taken place over time. That kind of stuff happens. All right, so there's this paper says limiting reactants, percent yield. In each of these examples, you've got a quantity of reactant, and you can predict how much product you should get, and then you compare the amount of product you should get to the amount of product you actually get, and just divide what you predict, or divide how much you get by the predicted amount, and that gets you the total percent yield for the reaction. I'll show you some real practical examples next week. We're gonna do a lab with limiting reactants, like limiting reactants and percent yield, so you can see how you actually get not the total amount of product that you expect to get as a result of the reaction that takes place. That's how life goes. I don't know. All right, so I don't know, you can work on this for the next minute or two or whatever, and then next week we'll go over those and do some more of that stuff. Don't come to school tomorrow. It's always weird and awkward on, well, like on in-service days, some people don't know it's in service and they'll come to school. There's always like a couple students get dropped off and it's totally awkward sauce. So I'll be like, they'll be like in the commons waiting. It's like 7 o'clock and I come in, I'm like, oh no. But I don't say anything to them because I don't want to be that person to break the news that like they accidentally came to school on an in-service day. There's always like somebody in the commons at like 7. And they're like, how come nobody else is showing up? There's no other buses.